me. We had looked at simple algebraic extensions. Algebraic extensions. So KA. I don't want to divide it. KA over K. So where A is algebraic over K. So then, in this case, we had seen that we had this result about extensions of field isomorphisms. So if A is algebraic over K, with minimum polynomial F, and phi from K to K prime is a field isomorphism. And we put F hat equal to E star of F, which just means that you apply phi to the coefficients of F. Okay, then and A prime and K prime is 0 of F hat. Then it exists unique field isomorphism phi from K of A to K prime. A prime, which is the identity, which is phi on K, so with phi restricted to K is small phi, and phi of A is equal to A prime. Okay, so this was this result, and we talked also about algebraic closure and other. And, but now I will want to continue with splitting fields, and then we will also prove some similar results in this context. So now we start a new splitting fields. So if K is a field and F is a polynomial in Kx, maybe non-constant, then we can find a field extension where we can first find a field extension such that F has a 0 in this bigger field, and then we can first find field extension L over K such that F has a 0 in L. So we can write, so I call this 0 A in L. Then we can write F is equal to x minus A times G, where G is element in Lx. In Lx, yeah. So, and so we can continue with this. We can now find maybe a field extension here of L such that that G has a 0 in the next field extension. So continuing like this, then we find the field extension so K over K such that F splits over K into linear factors, so that all its zeros lie in K. So I will carry this out, but anyway, so that's and the smallest such field with this property will be called the splitting field of F over small k. So let me work this out. So first I want to see that we can always find the field extension so that F is a 0. So this is the following theorem is cosmatic. Anyway, theorem. So let F be a polynomial with coefficients in K, in a field K, and we assume it's irreducible. So there exists a simple algebraic extension L over K such that F has a 0 in F. And in fact, we also have that the degree of L over K is equal to the degree of F. Okay, so in some sense we have already done this before. If we have a simple algebraic extension, we could describe it as isomorphic to Kx modulo sum F. And now we just turn this around to make this field by just defining this field extension L to be Kx modulo this F. So this will then be a field. So let me try to do this. So F is irreducible by assumption, and Kx is a principal ideal domain. So thus it follows that Kx modulo F is a field. Okay, and we want this to be our L. So I call it L. So now, if we look at, so we have the canonical projection from Kx to Kx modulo F, the canonical projection. And we can identify K with its image under pi. So certainly this map pi, if I restrict it to K, to the constant polynomials, will be injective. And so we find in the image will be isomorphic to K, we just identified with k, as we also always have identified constant polynomials with k. So that means k, so thus k is a subfield of L. Now I wanted to claim that it contains a zero of the polynomial f. What could that be? Actually, so we, as you can see, we have everything we have done here out of f. So it's somehow a tautological construction. So also the zero must be somehow tautological. So somehow out of thin air. And so I claim that the class of x is a zero. So claim x is a zero of f in f. For that, you just write it down. So f, you can write as sum I equals 0 to n ai times x to the I. So the ai are some elements in k. Now, let's look. We know if we take f, the polynomial f, and we take its class, modulo the ideal generated by f, this is obviously 0. Okay? So this will be the class of sum I equals 0 to n ai x to the I. So this bracket is just the map pi. Pi is a homomorphism, and so this will be, so it goes into the sum. And into the product, and also into powers. And now we have identified k with its image under this natural projection. That is, this class of ai is just ai. So this is equal to sum I equals 0 to n ai x to the I, which is f. Okay, so it's a bit okay, so that's just what it is. So by our definition, we have obtained the zero here. I should say it's, so somehow it's as you see, a formal construction, so we have somehow formally added a zero of this polynomial to our field to make it bigger. Now, the final, the statement, I also state that the degree is f, and that's kind of clear. So now so clearly we have that our field L can be obtained as K adjoining the class of X. No, because it's we just have added this one element in it. It's the same as adding polynomials in the class of X, and these are precisely the equivalent classes of polynomials in X modulo F. So this is a simple algebraic extent. So simple algebraic extension. And by normalizing F, putting the leading coefficient v1 and dividing the whole thing by the leading coefficient, we can assume that F is monic. F is irreducible, it is monic, and it has this thing as a zero, so it is the minimal polynomial of X. so therefore we see that the degree of the field extension is equal to the degree of the minimum polynomial. So somehow the same construction we had before when we had described simple algebraic extensions, we just turn it around. We now make it a definition. So thus the degree of L over K is equal to the degree of L. Okay, this was the statement. So as I said, we can say just as definition or way of saying, we say in this case L is obtained from K by adjoining formally a group of F. Now, as a corollary, we see that even if F is not irreducible, we always can find a field extension where it has a zero. So let F be an element in Kf of some positive degree, and greater than 0, there exists a field extension so L over K, so finite field extension of degree L over K equal small or equal to n, such that F has a 0. Has a 0 in F. Now the only difference to before is that we don't require F anymore to be irreducible, but we can just take any irreducible component of F and find a 0 of that. To apply the theorem to any irreducible component G of F. So we write F as a product of irreducible polynomials, and then obviously I take any one of them, the degree will at most be n, namely if the polynomial was irreducible to begin with, otherwise it's smaller, and so we get this. Okay, and now we want to, use this to make it clear where our polynomial splits by just kind of iterating this. But first, I define to you what we want to have, namely the splitting field, and then I'll show it always exists. So, definition. So we take any polynomial of some degree n greater than 0. I don't require irreducible or anything like that. A finite extension L over K is called a splitting field of F. If, well, there's two things. First, F should split over L into linear factors. So F splits over L. That means we can write F equal to B times x minus A1 times x minus AN, where B and A1 and AN are elements of the field L. So B is just, as I haven't required it to be monic, no? And that's the first thing, it should split, but it should also be somehow be a minimal extension with this property. So F does not split over any intermediate field. So L, so that means not L, F. So intermediate field means that K is strictly contained in F, strictly contained in F. So intermediate field just means that that F is somehow in between, but obviously, no, here I don't need that. So, but I mean, it doesn't split over any field which is really smaller than L. Obviously, by definition, also L is intermediate field, so I cannot exclude that. But okay.
But
so
this inclusion are in terms of embedding, or?
I mean, now, you know, like this, if I have a field extension, they are contained in each other, no?
But in the previous...
yeah, okay. I mean, so in the previous thing, I had identified this thing in the image. But okay, so that was just... So... Yeah, but I mean, it's... I mean... Yeah, now I don't know how to make this so super clean. I mean, you could always say, if you know, you have this you know, if you want to be, you know, in the previous theorem, if you want to be precisely the K a subset of this thing, you take this this quotient and the elements in the image of K goes to the thing, you replace by the elements of K. You know? I mean, if you really want to be super precise. You know? And then, you know, you have a field which contains K as a subset. Okay. So there's no obstruction. Anyway, you can do it. So, we first want to show that these splitting fields always exist. Later we will show that also in some sense they are also unique. So this is the following corollary of what we did above. So we take, so for simplicity maybe I assume, well, you have to do that. Yeah, well. So if I wish again, I can make F monic by dividing by the leading term, so maybe I do that. So let F in Kx monic of positive degree. So first, if I have an extension L over K, be an extension such that F splits in L. That means that I can write F equal to x minus A1 times x minus AN. Actually, I didn't need it really want it. Yeah, maybe I just say that of degree n bigger than 0, so like this. Then so where A1 or AN are elements in L. Note that by definition B is an element in K because it's the leading coefficient. Then if I take K, A1 to AN, which by definition is a subfield of L, is a splitting field of F over K. I should maybe insist a little bit, so I say here it's the splitting field of F over K. So it doesn't only depend on F, but it also depends on K. Because the splitting field by definition has to contain K. So it's an extension of K. If I make K bigger, then also the splitting field has to become bigger because it has to contain all of K. So it's not just the splitting field of F. No, you could, if F has coefficients here, I could still view a splitting field over a much bigger field. And it would be maybe something different. Anyway, but now we get to this. So this was the first statement. So we just obtained the splitting field by adding to our original field all the roots of the polynomial in some extension. So then there exists a splitting field. Of F over K. So L, well, maybe it's not L, F of F over K, and its degree, the degree of F over K is smaller or equal to n factorial. So n times n minus 1 and so on. And the third statement is so that's what I just talked about. So if you extend, what happens if you make this field bigger? So let but now in a different way, so that K be a splitting field of F over small k, and let L be an intermediate field. Then K is also a splitting field of F over L. So that's in some sense maybe clear. So if you make this field bigger, but so that it's still contained in the splitting field of the original polynomial, the splitting field stays the same. Okay, but okay, so this is the last. This is almost by definition, but let us prove this now. So we want to show one. So we assume that L over K, that we have this extension L over K such that F splits over L in this form. So then clearly F splits over K A1 to AN, because we can write over this field, we can write it as this product. So we have to see the second statement, namely that it doesn't split over any intermediate field. So assume, so let K, not K, F contained in this KA1 to AN be a subfield containing K to an intermediate field such that F splits over F. Over large F. So that means we can write F equal x minus C1, or maybe the coefficient is the same, b times x minus C1 times and so on times x minus Cn, where the Ci are elements of F. But then, obviously, if you think of it, this would imply that the Ci's are actually equal to the Ai's, as we can see if we just put, if we just try to evaluate this with AI. So then for all E, we have that F of AI is equal to AI minus C1 times AI minus Cn, and we know this is equal to 0, because so we have still have this P, which also we have kept. And so how this can only be possible, as we are here in a field, if at least one of the factors is 0. P is not 0, so thus it follows there exists an I such that, maybe I call it a J, such that AI is equal to Cj. For some J. But Cj is in F, so every AI is in F. For all I. Thus it follows that K, A1 to AN is contained in F. So that means, so F is contained in K1 to N, but also conversely, so they're equal. So now, the second statement is kind of clear. We just kind of join elements one after the other. And so we make kind of, so by the corollary before, we have that there exists a field extension L1 over K such that F has a 0 A1 in L1, and so thus we can write, as I sketched before, F is equal to x minus A1 times G, with G polynomial with coefficients in L1, and now we can make induction over the degree of So, and obviously, so f was having degree n. So we have exists such a thing with the degree of L1 over k is smaller or equal to n. N is the degree of f. And the degree of G is smaller or equal to n1, is equal to n1, n minus 1. No? We just divide by it. So we can now use induction over the degree of n. Obviously, the degree of f is 1, the statement is trivial, so the start of induction is trivial. And so so now we have that the degree of we want. So by induction, on the degree of f, there exists an extension, say f over L1 of degree L over L1 smaller or equal to n minus 1 factorial, such that G splits over L, and thus F splits over L1 over F 2. Oh, so thus we can write F is equal to B times x minus a1 until x minus an with well, maybe I can first say this here. So then thus, if I look at the degree of L over K, this is equal to the degree of L over L1 times the degree of L1 over K, which is smaller or equal to, here the degree was at most n minus 1 factorial, here the degree was at most n, so the total degree is at most n factorial, and f splits, so we can write f equal to b times x minus a1 times x minus an with the ai elements of L. So thus, by part 1, we have that k a1 to an is a splitting field. Of f over k. And obviously its degree is at most as big as the degree of L over k because it is contained in F. So f k a1 to the n is a subfield of L. We get also that k a1 to a n over k is smaller or equal to n factorial. Okay, so this was the second part, and the third part is actually, which there is actually trivial, because so clearly by definition F splits over this L here, because it's no, F splits over K, because F splits over K. No, K was a splitting field, so F splits over K. It doesn't depend on whether K is viewed as an extension of L or of K, of small k. Really, F splits over K. And obviously, it does not split over any intermediate field between small k and large k. So, in particular, it doesn't split over any intermediate field between L and large k, because this field is bigger. There are less intermediate fields. Okay, so this is here. So this is the extension. So let's look at some. I just have a few examples so that one can see the different things that can happen. I think. No, that's fine. I think it's maybe better if I divide it in half, so maybe I do that now. No, it's more of like to give myself more space. So let's look at some examples.
So I don't see how it follows the conclusion from
For which one?
3.
Okay. So the definition of a splitting field is The definition of a splitting field is that for polynomial f over some field is that f splits over the splitting field, and it doesn't split over any smaller intermediate field between the field you start with and the splitting field. Now, if we make the field we start with larger but still contained in the splitting field, then obviously the same f will still split over this bigger field because it's split before, it's the same f, and it doesn't split over any intermediate field between this intermediate field and this, because it's just a tautology. There's nothing. So, okay, let's look at some simple examples. So if we take q square root of 2, this would be a splitting field of x squared minus 2. If we take the square root of 2 out of the corresponding complex numbers. So more generally, if f in the x is irreducible of degree 2, and alpha in L is the root of f, so f of alpha is equal to 0, then k alpha is a splitting field of f over k. No? Because once you have one root, you also have the other, and but you do need the root in the splitting field, so this is the splitting field in the same way here. So by definition. So you can look at the slightly more complicated query, so let's look at the splitting field of, say just now we take Q of x to the third minus 2, so over Q. So in this case, we can first, if we want, add this third root of 2. So over Q, third root of 2, this thing will have a 0. F has a 0, namely third root of 2 is a 0, but it does not split. For instance, you can see this if you work with complex analysis, that the roots over the complex numbers will be third root of 2, third root of unity times third root of 2 and the square of that. So, so over C, and the roots of this polynomial are third root of 2, theta times third root of 2 and theta squared times third root of 2, where theta is e to the 2 pi I divided by 3. So you can see that theta is not a real number, so therefore we can certainly, it's not contained in this. So, or theta square root of 2, not an element in R. It cannot be. In fact, we can easily say what the minimal polynomial of this thing is. So is x squared plus x plus 1. Because you can see that if you take the sum of these, theta plus theta squared plus theta plus 1, this will be 0. Now you can either see this directly, or you can see that this is, well, and I think you can check that. So thus, the degree of Q theta, so this is both, say, theta third root of 2 this degree is equal to 2. Because this, we know that the theta does not lie here, so this must be reducible. So, and clearly this thing itself is equal to Q theta, so third root of 2 theta third root of 2 and theta squared third root of 2. Because if you have these two elements, then clearly you can multiply them, this one with theta and this one with theta squared, you get these. So this is one inclusion, and on the other hand, if you have just these two elements, you can divide by one by the other, you get the theta. So you know that these two fields are the same. So thus, this thing, Q zeta square root of 2 is a splitting field of this thing x to the third minus 2 over q. And we see that the degree of this thing over q is equal to, so we first, the first extension has degree 3, this was useful, and then we take an extension of degree 2, so this is 3 times 2 equal to 6. So we had seen that the degree of the splitting field is at most n factorial, where n is the degree of the polynomial. So in this case, precisely n factorial. 2 factorial is 2, 3 factorial is 6. So that's fine. But now let's look at an example where this is quite different. So we look at the splitting field of x to the 4 plus 1 over q. You can check as an exercise that this is very useful. I don't know whether any of the standard criteria apply, I don't think so, but if you just write down, if it's splitting, so that you can easily see this will not have 0, and then if you try to write as a product of two polynomials of degree 2 with arbitrary, variables as coefficients and try to find them, you find out that it's impossible. Okay? So, and we look at this. So let alpha be a root of this polynomial, we call it in f, in an extension Q. For instance, if we want to work inside the complex numbers, we could put alpha to be, this somehow a square root of I, where I is the complex thing. So this would be e to the pi I divided by 4. So, if alpha be such a root, then what can we say? Then, by definition, it follows that minus alpha, 1 over alpha, and minus 1 over alpha are also roots of f in this extension. Because L is a field, so if it contains alpha, it contains also these. And we can also see they are all different. So clearly alpha is different from minus alpha because alpha is not 0. No? And alpha is also different from plus minus 1 over alpha because otherwise I could multiply this thing by alpha, because if alpha squared is equal to plus minus 1, then it follows that alpha squared, alpha to the 4th, plus 1 is equal to 1 plus 1 is equal to 2, which is certainly different from 0. So these are all distinct. So thus the splitting field of x to the 4 plus 1 over q is q alpha. And as this polynomial, this is now a simple algebra extension, and this thing is its minimal polynomial, so we have the degree of q alpha over q is equal to 4, which is obviously much smaller than 4 factorial. So it somehow depends on the field extension, on what precisely the polynomial is, how big the splitting field has to be. Okay. Even so, if the polynomial is irreducible, the degree must be at least the degree of the polynomial, and it's at most the factorial of that. So there's a lot of room, and this somehow tells us something about how complicated this polynomial is in certain ways. Okay. Now we want to come back to this extension of field extensions, of homomorphisms, of field homomorphisms in field extensions. And we do this now for splitting fields. So before we had the statements, if you have a homomorphism between simple algebra between two fields, then it extends to the corresponding simple algebra extensions in a unique way, if one says precisely what I now hinted, yes?
Why did we show that they are all different, the roots?
Why?
Yes. I mean, this helps to show something else, or we did that?
No, but with this now I have 4 roots. I have a polynomial of degree 4. If it would be, if 2 of these roots would be, if these would be, some of these would be the same, I would in fact have only, for instance, assume they are pairwise the same. Then in fact I've only given you 2 roots, and so I have not split you the polynomial. I don't know then that I'm in a splitting field. No, but here I have now, so I have alpha minus alpha 1 over alpha minus 1 over alpha are 4 roots over this thing, so it splits into linear factors. So I actually know that x to the 4 minus 1 as it's plus 1 as its monics is just x minus alpha times x plus alpha times x minus 1 over alpha times x plus 1 over alpha. Because it cannot, because it is monic, and so it has to have this form.
There can be different non-isomorphic splitting fields.
Yeah, well, that will be the next thing we. And so from the thing that I'm now going to show, it will follow that all splitting fields are isomorphic. Now, obviously, the splitting field is not uniquely determined as a field, because by the definition it's only well defined up to isomorphism. But I also will claim here that a splitting field of polynomial f over k is well defined up to k isomorphism. Okay, but this will follow from what I say now. Once I have it. Yeah. It was actually the next sentence I wanted to say, but anyway, now I have already said it, so let me first state the theorem. So extension of homomorphisms to splitting fields or isomorphisms to splitting fields. So assume, so first I have to do it in the biggest generality because this serves in some proofs, but then most of the time one is only interested in special cases, so let phi from k So K prime, then isomorphism of fields. So we take polynomial okay, the polynomial and we put f hat say to be phi star of f in K prime of x. Remember, phi lower star of this just means to apply phi to the coefficient of the polynomial. No, sum ai x to the I goes to sum phi of ai x to the I. So let me take this. And we look at splitting fields. Let K be a splitting field of f over K, and in the same way let say K hat be a splitting field of f hat over K prime. It's a little bit most likely confused with the head and the primes, but anyway. So then what? Obviously then I want that K and K hat are isomorphic by an isomorphism which extends our phi. Then there exists an isomorphism large phi from K to K hat which extends our phi, so with large phi restricted to K, now viewed as a map from K to K prime is equal to phi. Okay, so this is the statement. So obviously it follows as required before that let the corollary let L prime maybe L hat the splitting fields. I will so L prime the splitting fields of a polynomial f over K, then there is the K isomorphism P from L to L prime, which is just a special case where small k is equal to K prime and phi is the identity. No? Then it's precisely this thing. So in particular, as you see, the splitting fields are very defined up to isomorphism. Okay, let me first prove it and then comment. So we want to make an induction over the degree of large K over small k. So if this degree is 1, then it means then large k is equal to small k, and thus our f so follows that f splits over k, thus it follows that f hat splits over k hat, k prime, and so it's fine. So we just we have our phi large phi is equal to the small phi. So and k prime is the split into of f over k prime. So that's the trivial case. Now let's make the induction. So we assume that the degree of k over k, large k over small k, is bigger than that. So that means f must have an irreducible factor of degree at bigger than 1. V of t is bigger than 1. So it follows, as this p star here sending just the coefficients via p is an isomorphism from k of x to k prime of x prime, it follows that thus if I call g hat equal to phi star of g is an irreducible factor of f hat, obviously of the same degree. Okay, so now we can. So now what we want to do? We want to make this induction by reducing it to our previous result. We know how this works for simple algebraic extensions. So we take a 0 of this thing, and then we apply take the field extension given by that, so 0 of this g, and then we apply our previous result, and this will imply it by induction. So let A be 0 of G in K, and then A prime is 0 of G hat in K hat, I think. Then by previous extension result, so there exists a unique isomorphism P tilde from K of A to K prime of A prime with phi tilde restricted to K without any phi. So now, obviously, we also have that the degree of K over Ka is strictly smaller than the degree of K over small k. Because this has, here the degree was, the degree of this over this is at least 2, so this is at most half of this. So by induction, and we have that the field extension K over Ka is, and K is a splitting field of F over Ka, and K hat is a splitting field of, what was it, F hat over K prime. No, this was just the thing. It's always what? What? What?
K prime, A prime.
Yeah. What over? Yeah. K prime, E prime. That's that's the usual thing. Sometimes forget. There's something. So therefore we are in the same situation as in the theorem, but now the degree of the field extension is smaller, so we can apply induction hypothesis. So thus, by induction, and there exists field isomorphism phi from K to K hat with phi restricted to the smaller field here is equal to this phi tilde. So therefore, if I restrict it further to K, I get the phi. Okay, so this is the proof. So, you see, so we haven't really very much tried to understand how many extensions there might be. We just kind of make this induction where we just choose one and then say the rest follows by induction. So I should maybe say this. So note, there is no uniqueness statement. We just have that there's the existence of such an extension. But we have no idea how many extensions there are. This is actually important, so this is something we really do not know, and which somehow is an important restriction in what we understand. So because we will finally want to understand things in terms of such isomorphisms, and so if we don't know precisely how many there are, so we have somewhat restricted knowledge, and so the whole difficulty of the subject is somehow related to this, that we cannot say how many, for instance, one of the statements was this thing I just, anyway. Anyway, so we will come back to this. So that, so before, when we were talking about simple algebraic extensions, we knew that for every root of, so if you have the simple algebraic extension given by one like one given one element. If we take the minimal polynomial, then there is for every root of the kind of transformed minimal polynomial in this other field, there is a unique extension of the map. Or if I talk about the same field, if you have if you have a simple algebraic extension, then for every, if you are giving yourself a root of the minimal polynomial, then for every other root of the minimal polynomial there's a unique unique k-homomorphism of the bigger field, which sends the first root to the second. So we have precise descriptions of how many there are. In this case, we just say there are some. So that's the difference. Okay, so now let's look. Where am I? So now we will. So we want to do Galois theory, which is will be somehow the study of Galois extensions. So Galois extensions are field extensions which are particularly nice. And being particularly nice means that they have two nice properties. One is called they are normal, and another one is called they are separable. And so we have to look what these two things are. So I want to study Galois extensions. So which by definition are extensions which are normal and separable. So we have to study these properties. So we start with normal extensions. So it's actually the definition is looks a bit crazy and nonsensical, but it's what it is. But then we'll see in a moment that one proves then that an extension is a normal extension if and only if the bigger field is a splitting field of a polynomial with coefficients in the smaller field. So first, so definition is not very intuitive. So let me first say the definition, which we will also need, but at least so an algebraic field extension is called normal if the following holds. So if every irreducible polynomial, so I should maybe say the field extension is again L over K. If every irreducible polynomial f with coefficients in K, which has a zero in the bigger field, already splits over L into linear factors. So now if you think of it for a short moment, it seems unlikely that such things can even exist. No, and why should that be the case? You have a field extension And you should have the property that whenever you have a polynomial with coefficients in the smaller field, which has a 0 in the bigger field, it already splits into linear factors. And it seems like a very unlikely property, but now we'll see that this actually does happen, and it happens essentially if and only if the bigger field is the splitting field of a polynomial with coefficients in the smaller field. I mean, just first as an example, if we look at the field extension q third root of 2 over q, this is not normal. As we have already seen, because if we look at the polynomial x to the third minus 2, has a 0 in q third root of 2, but does not split. Okay. So now we come to this result. Not sure, but I can just start. It's actually a bit so. So if I assume the extension is finite, the finite extension L over k is normal, if and only if L is a splitting field of a polynomial, say f in here. So this is somehow quite non-obvious if you think of it. So why should that be the case? Because you split one field, one polynomial. All polynomials which have a 0 should split into linear factors. Seems kind of unlikely, but we will see why it's the case. So the interesting direction is this one, obviously, because that seems kind of unlikely to be true. So let L be a splitting field of some polynomial f in X. So now this is a different f than here. So now we want to record this thing here g. So polynomial. So let g be a polynomial kx be irreducible with a 0 alpha in f. So we have to show G splits over F. So all its zeros over any extension already has the line F. So let beta be a 0 of G in an extension of F. So we know that if we can always add zeros until it splits into linear factors, but what we need is that the zeros finally end up lying in L. It splits already over L and not over some extension. We have to show that beta is an element in F. So then, by induction over the root, so we do this for all roots, so we see that all roots lie in L, so L splits, so G splits over F. So then it follows by induction over all roots, G splits over F. So now Okay, still we don't know why it should be true, but now we will use this story with these extensions of field isomorphisms in a somewhat surprising way. So G is irreducible. So thus we can assume that G is monic. So it is a minimal polynomial of alpha over K. So thus by extension of field isomorphisms in simple algebraic extensions, we have that there exists a map, say phi from K alpha to K beta, which is a K isomorphism. No? So this, we extend the identity. So we have, this is a root of this minimal polynomial somewhere. This is then another root of the minimal polynomial. So there exists such an isomorphism by this result. So now L is also a splitting field of K alpha of L or of F over K alpha. No, because alpha was already in L, so this is it's a splitting field over an intermediate extension. And L beta is a splitting field of F over K beta. So what does that mean? So this is maybe less obvious. So certainly F still splits, it splits over L, so it splits over L beta, but clearly it cannot split over any intermediate field between L beta and K beta, because this thing, this L will be the field which is generated by the roots of F, and this will be the field which is generated by the roots of F and beta, because it has to contain beta. No, the splitting field of F over this thing is a field which contains K beta, and the smallest field which does this and is a splitting field is L beta. Okay, so note that so if L is equal to K A1 to AN, where these are the roots of F, then this will be K beta A1 to AN. And so we know that if you join the splitting field you obtain from the given field by adding all the roots. Okay. So now we can again use the extension of field isomorphisms. So by extension of field isomorphisms, now in the splitting fields, there is an isomorphism large phi from L to L beta, because they are both splitting field, which extends this isomorphism here. was a K isomorphism. So if I restrict it further to K, we get the identity. So that means that phi is a K isomorphism. Large phi is a K isomorphism. So thus, phi from what was it, L to L beta is a K isomorphism. So in particular, it's an isomorphism of vector spaces, of K vector spaces. So it follows that the degree of L over K is equal to the degree of L beta over K. And therefore, by the degree theorem, we get that the degree of L beta over L is equal to 1. So that means L beta is equal to L. So we have with these, in this kind of crazy way, we have obtained that after this whole story, by using this isomorphism, we finally find this is equal to L, so beta is an element. And this is what we want to show. Okay? So maybe, I will maybe slightly review it. The next time the converse direction I maybe do on Monday or whenever we meet again, and also briefly, you can also maybe ask me about this. Okay, so thank you.